In this video, we're going to introduce fluid mechanics, and we're going to define pressure, density, and also obtain an equation for the variation of pressure with respect to depth. Now, fluids are, unlike solids, do not have a fixed shape. That means, at least unlike rigid bodies, do not have a fixed shape. And what we'll say is that all our fluids are going to have an important property of being incompressible, and we'll base a lot of things on this idea. Okay. Very quickly, let us define what density is for any object, and density denoted by the symbol, the Greek letter rho, or HO, is equal to mass divided by volume, mass per unit volume, and so its units are nothing but kg per meter cube. Okay, and the densities of typical materials are the density of water is equal to, so this is all about density. The density of water is equal to 1000 kg per meter cube. Then the density of mercury is 13,600 kg per meter cube. The density of air is 1.29 kg per meter cube, and these are some of the accepted values. Okay, what we'll do next is we'll define pressure, and pressure is nothing but pressure denoted by the symbol P is equal to the force per unit area. Okay, we measure pressure in newtons per meter, but it's a fairly important quantity, so it has its own unit. We call it the pascals. Okay, now think about, if you're standing on your 2 feet, you feel a certain amount of pressure on your on your feet, and then when you get on your toes, you stand on your toes instead, the pressure has increased because the surface area of contact has decreased. Okay, so pressure is force per unit area, and since the area goes down from when your entire feet are touching the ground, the surface area that the force is exerted on is larger, and when you go on your toes, it ends up being a small area, and so the pressure itself increases. Okay, at the same time, if you were to stand on a nail, then the pressure would be very, very high. It would be very painful. But at the same time, you can lay down on a bed of nails, and just the amount of pressure now decreases because if the bed of nails has 10,000 nails, then what you've done is you've taken that pressure and you've spread it over, or rather you've increased the surface area by 10,000, so you've decreased the force by 10,000. Okay, so that's simply pressure, which is nothing but force divided by the area. Now, what we'd like to do is figure out how pressure changes with depth. So pressure variation with depth. So let's figure this out. Let's figure out how much the pressure, or how the pressure changes with depth in a liquid. Okay, so let us take a container that has a certain amount of liquid. Let the density of the liquid be rho. Okay, and what we'd like to know is what is the pressure at any depth h. Okay, now I want to point out that this h, I know we've used h for height and all that, but we're going to use it for depth here. We're not going to put the negative sign, so please do not make the mistake of writing a negative sign when you try to obtain h here. H is going to be the height below the liquid. Okay, so that's the depth of the liquid, and our goal is to find the pressure at this point. So what we'll do is we're going to go back to our definition of force, which is pressure, which is nothing but force per unit area. And what we'll do is we'll say that, okay, let us find the force, okay, that is exerted on some area A. Okay, and due to everything that's above it. So we can basically consider a column, okay, of material that goes above it, and we can ask, hey, how much force is exerted on this area? What is the total force that is exerted on this area? And once we know that total force, we can divide it by the area and obtain the pressure with respect to the depth h. Okay, so here's what we'll do. We can take this area, okay, and we, again, that's our goal. So we ask the question, at the surface of the liquid, okay, is there any pressure? And what we know is, when you're not inside the liquid, when you're outside the liquid, there is some pressure, and that pressure is due to all the atmosphere that's above you. Okay, so in blue, I write down, I just represent rather the atmospheric pressure. Okay, we're just going to call it P0, and this will be the atmospheric pressure. Alright, great. So we know that that's the atmospheric pressure. So we can find the force due to the atmosphere on the surface area A, okay, which will be nothing but P0 times A. Now, all we need to do is now figure out the pressure, or rather the force first, due to this liquid, okay, within this container. And if we can figure out the force due to this liquid, then we'll be very close to our answer. So let's write all this down. So what I'm going to do is, first I'm going to find the force. The total force is equal to the force due to the atmosphere plus the force due to the liquid. Okay, so these are the two things that are exerting the force. Now, the force due to the atmosphere is equal to the pressure due to the atmosphere multiplied by the area. We know this because we know that P is F over A. Okay, so that's the reason why we get this. Now, plus we'll find the force due to the liquid. Now, the force due to the liquid, if you see, is nothing but the weight of the liquid. So this is W representing the weight of the liquid. Okay, now we know how to find the weight. Weight is equal to mass of the liquid multiplied by G. Okay, so the first term remains the same. Now we want to ask, what is the mass of the liquid? Now mass is nothing but the density of the liquid multiplied by the volume. So it is rho times V times G. Now we can ask, what is the volume? If you look at this right structure, the area of the base is A and the height is H, and we know that for all these things, the volume is nothing but the area of the base multiplied by the height. So now we have the volume and multiplied by G. Great. So you see, what we can do now is, from this force we can factor out the area. So force is equal to area times P0 plus rho G H. And now what we know is that the total force, the pressure is nothing but the force divided by the area. So this F over A, and so this ends up being nothing but P0 plus rho G H, all this multiplied by A and divided by A. The A cancels out and we get the pressure in this beautiful equation. Okay, now understand this, that this is the equation for pressure at a depth for a fluid that is not moving. Okay, this is very important. So make note that the fluid is static. Now when the fluid is actually going to start flowing, that'll be the last part of this chapter. At that point we'll have a different expression for the pressure. So please do not confuse between the two. Okay. Also, let's understand what each of the terms here are called now. P has a name. It is called the absolute pressure. So P is the absolute pressure. Okay, so it is the total pressure due to the atmosphere and the liquid. P0, we already know, is nothing but the atmospheric pressure. Now the accepted value for this pressure is 1.01 times 10 to the 5 pascals. Now this value actually is going to change. It depends on the temperature, it depends on many things. But for our things, we'll just assume this to be the value unless otherwise stated. The term rho GH is nothing but the pressure due to the liquid. Okay, if you look at this is the pressure due to the liquid. Okay, and it has a special name. It's called the gauge pressure. So understand this. we have the total thing is the pressure due to the atmosphere plus the pressure due to the liquid. Okay, and this particular, the rho gh term has a special name. It is called the gauge pressure. Okay, in the next video, what we'll do is we'll try to solve some problem, apply this concept to some simple problems.